Can we see who is joined here? No.
Then how can you share your screen? You are familiar with it.
Yeah, but you need to unshare first, right?
Not just share.
It's your screen is being shared.
Yes.
When you will unshare, then I will share.
Yes.
Right?
Yes.
Yeah. So I have to wait for you to unshare. I just said maybe we can take a look at this. No open questions. Okay, there is nobody here. So the echo is gone now, right? Echo. Oh, you are muted now. So when you speak, you will unmute, right?
Yes, I will use this one.
Yeah. Oh, you will use this one.
Yes.
Good idea.
Yes.
Assalamu alaikum. How are you, Amir?
Good
to see you.
What you?
Is this your first time visiting us here?
Yeah, very nice center.
Ah, thank you, thank you.
Pretty cool, yeah.
Yeah, always good. Why didn't we enable the other cam? I think you're using the TV cam.
The TV, yes.
So that you can zoom on to him.
I think that we discussed with the technician probably there's some USB cable thing that needs to be done, and we said it's probably last minute.
Really?
Yes.
Yeah, that's why we felt so calm.
I think that's fine.
No, it's fine. This is easy. It's very easy. That's fine. We still have time. We still have time. So what's the?
It is recorded.
It's fine. Let's just make sure that it's the webcam is.
So this is the microphone?
Should be, but if it is enabled, I'm not sure what's happening here. Let me just quickly double check this as well. Just remove one. Muted. Let me see if it's actually.
Working now?
I think so. Which you're sharing what? The slides?
I shared this small slide.
So the microphone is working now? Okay.
Is it working? The mic is working.
Probably. Is it working? I'm not sure. Is it working?
Yes, yes, you can see the signal.
Okay.
Yes, your mic is working. Let's get started.
I am.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone and thank you very much for joining our today webinar. I am Dr. Saddam Al-Azzani, Research Scientist 3 at SDAIA-KFUPM Joint Research Center for Artificial Intelligence, and I will be moderating today's session. Kindly be informed this webinar is organized by SDAIA-KFUPM Joint Research Center for Artificial Intelligence and facilitated by KICS. Today we have an interesting topic titled Physics-Informed Machine Learning for Seismic Modeling and Inversion. And our today speaker is Dr. Umar bin Wahid. Dr. Umar bin Wahid is an associate professor of geophysics at King Fahd University of Petroleum and Minerals, KFUPM. His research interests are broadly the area of computational geoscience. He is an author of more than 110 publications. Dr. Umar graduated from King Abdullah University of Science and Technology with a PhD in Earth Science and Engineering in 2015. Prior to joining KFUPM in 2017, he was a postdoctoral fellow at the Department of Geosciences, Princeton University, and a writing in science and engineering fellow at the Princeton writing program. Dr. Umar received the Early Career Researcher Award at King Fahd University of Petroleum and Minerals in 2022. He is the 2023 Society of Economic Geologists ESG honorary lecturer on the topic of physics-informed machine learning applied to geophysics. Kindly be informed that you will be muted during this webinar. And if you have any question, please just drop your questions in the question box, which will be answered at the end of this webinar. Dr. Umar, please go ahead. The floor is yours.
All right. Thank you, Saddam. So I have to share my screen here. Let me share this.
It's easier to share the PowerPoint, not the entire screen.
Okay. All right. Thank you so much, Saddam, for the introduction, and thank you, Dr. Mutaz, for hosting the talk. I trust that all of you online are able to view the screen to hear me as well. If not, probably you can send a message. Zoom quick.
Do not send.
It's still working?
Yes.
Yes.
Okay. Perfect. Yeah. All right. Thank you, both of you gentlemen. And I'm going to.
I think you need to redo that. Apologies about this.
What we need to redo that.
Share.
The screen. Okay.
All is good from your side, Saddam?
Yes.
Yes.
Okay, things are working. Okay, I hope all of you online are able to now view the slides and are also able to hear me. If not, you can send a message in the chat, and probably Saddam will take action based on that. So the topic for today is physics-informed machine learning for seismic modeling and inversion. So even though I'm going to talk about applications in the area of seismic modeling and inversion, but hopefully the talk will have some relevance for all of you who are interested in the general topic of computational science and engineering, and also those of you who are interested in the area of machine learning, okay? So I try to make some connection with broader areas of computer science and engineering when I go on and talk about my different topics. So let me go ahead and start the talk. Okay, so Saddam did a pretty good job in introducing me, and I think that's all. However, I think I should mention I will at some point have 110 journal publications, not yet. Okay, Saddam, so I think that was not correct information. But anyway, other than that, thank you so much. So I'm just going to start by introducing this other, I think, session that is happening, very relevant to talk today. It's tomorrow by Dr. Fahad. So all of you who are listening, please register for this event as well. I believe this will be a very exciting and interesting, let's say, seminar series as well. All right, my group, we're essentially working on two problems. So one on the left that you see here, let me see if I can find it.
There has to be a map somewhere.
So this one is working, but I'm not sure. Yeah. Can we get this? Oh, there's.
Yes.
Okay. All right. So this thing left we see here, the thing that we work on is trying to understand how seismic waves propagate in the subsurface, and so that we can use that information to understand the properties of the subsurface. So do a lot of machine learning based algorithms to try to understand wave propagation of these waves inside the earth, and also, you know, develop some algorithms that use that information that is received on the surface to build some subsurface model. The other thing that my group and I are interested in is understanding and mitigating the hazard of induced seismicity, which can be caused by many industrial operations, including hydrocarbon storage and extraction. And nowadays, with interest in going carbon neutral, these applications such as CO2 sequestration or geothermal energy exploitation in mining are also causing new sources of induced seismicity. So we try to develop algorithms that can enable us to, let's say, better understand and mitigate the seismicity by developing real-time monitoring solutions. So those are the two topics that I'm going to talk about today. But first, I'd like to introduce to you some of the research outcomes that have come from my group in the recent past. Okay, the first thing that I want to mention briefly here is this topic where we tried to develop an algorithm to detect induced seismicity in the area of Groningen in the Netherlands. So Groningen is the let's say the biggest gas field in Western Europe. It's been producing since the 1960s. However, induced seismicity started to be observed in the 1990s. It grew in terms of its frequency and the magnitude to the point that it created a lot of, let's say, social unrests in the Netherlands, and there were protests. Some of you may have heard of it, and then it led to the Netherlands government deciding to shut down production, resulting in a huge, let's say, loss of financial loss for the country, and also, in terms of creating a lot of, let's say, damage claims for the people who were in there. So the Netherlands government decided to share all the data coming from this area so that we can understand what was going on, and therefore researchers could study and hopefully in the future mitigate the series of events that led to this happening, right? So the biggest problem in identifying this induced seismicity is that, unlike the earthquake we recently witnessed in Turkey, which had a huge magnitude and caused a lot of destruction, these events, induced seismic events, are much lower in magnitude. They can be at times only felt, and sometimes they appear as cracks in the buildings and minor shaking, which sometimes people will not feel, or it may not cause damage to the infrastructure, or it may not cause damage to loss of lives, etc. But it can be, it can make people nervous. And therefore, what we did here was that we tried to train our convolutional neural network. Let me see again. Finding the map is not easy. Okay, anyway, I don't know where it is, but what we did here was to try to detect on, let's say, sensor network, shallow borehole sensor network. So if you have something like this indicated with red, which is something that is coming from the subsurface, then it will appear first at the bottommost sensor, and then it travels upwards. If you look at the seismogram shown here on the top, so you see the event first arrives at the bottommost sensor, indicated by that red vertical line, and then it travels upward. That indicates something that originated in the subsurface versus something that originated on the surface would appear as something that energy that appears first on the topmost sensor, which is shown by the green inverted triangle, and then it travels downward, right? So that's the thing that we use. So typically, if you look at deep learning literature in cosmology, people would look at a single sensor, and they would try to detect whether it's an event, a true induced seismic event, or it is noise. So if you look at just one sensor on these, let's say, sensor networks, you will see both of them look like it has energy, and it's not easy to make the distinction. And therefore, by using or by creating such examples to train a convolutional neural network to identify such patterns and distinguish between a true event and noise originating from the subsurface. Sorry, from the surface. Another thing that we did, and this is in the field of rock physics, the idea here is that people try to scan these rock samples, and they try to predict properties of these rocks, such as porosity and permeability. But the scanning time that is needed to create a good quality image, something like what you see in the middle here, takes time. For example, it took 1 second to scan this sample. Now, that's too long to study dynamic phenomena like core flooding, for example, which happens really on the order of much less time than 1 second. And therefore, the idea here is to train a convolutional network with some kind of a crappy image on the left, which can be scanned faster than 1 second, and then learn the mapping from this bad quality image to the quality image. And what you see on the right is the result of our trained CNN denoising, and it shows, let's say, much better predictions than the one we see in the middle, even because it can also filter out some noise that is present in a label set. All right, another thing that we're working on, we are also collaborating on this with Dr. Mutaz and Dr. Saddam on this. So this is trying to automate the work that geologists do, right? So geology is a very visual field. And if you see how geologists work, they basically look at these rocks visually and try to make some analysis based on their past knowledge that they've accrued over the years, right? So this is a very tedious job, and it takes hours of work. And sometimes, your predictions or your analysis or in the morning is different than what you would do at 4 p.m., right? When you're worried that your wife is waiting for you and you have to leave fast, okay? So there's this sense of inconsistency in terms of predictions by humans, right? That is always associated with human interpretation. And therefore, we're trying to produce something based on, different aspects of machine learning or deep learning that can do these tasks in a fast, accurate, and consistent manner. And eventually, we want to put together a phone app that these geologists can take with them to the field, and in real time, they could get some predictions and base maybe their field trips on those decisions, right? On the right, you see an example of object detection of these sedimentary of these core structures for these sedimentary layers. All right, so far what I've shown you all is purely data-driven machine learning methods or deep learning methods, right? So you collect a bunch of data, you throw that data to the algorithm, hope that it will eventually learn what's the relationship between the input and the output, right? However, Something like this was tried also by Google in the past to predict the onset of flu, essentially based on just the let's say the queries on Google. So without taking into account the dynamics of disease propagation or disease spread. So essentially, if a lot of people are searching for flu, it means that there is an onset of flu, right? So it worked really well until the period, it was being trained, but then it started overestimating, and to the point that it was taken down. And look online, you will find many examples or many articles where it says that there are many problems with purely data-driven approaches. And one such example is, let me see if it works. It's not yet. Okay, is this example coming from a soccer game in Scotland? There was an AI controller that was supposed to control the movement of the camera. Is it working now, those?
I'm not seeing it.
Okay, anyway, so I'll try. So this AI controller was supposed to, track the movement of the ball, and it kept switching between the ball and the ball referee. Okay, because it thought this is the ball, right? And while we may, laugh at this thing, the consequences of such mistakes can be catastrophic when it comes to medical diagnosis, self-driving cars, right? So the point here is that we need to understand our physical system better and somehow embed that knowledge into these machine learning models. And that's the topic for today, right? So all of us who have been in the field of computational science and engineering, and not necessarily in computational geophysics, I'm sure many of the audience line would be working with different form of computational science and engineering problems. So we have been in this domain tradition, right? Where we have lots of physics and very little data. Right? And we built finite difference or finite element algorithms to solve our partial differential equations, to do the forward modeling, or solve inverse terms. Now, all of a sudden, in the past decade, or we are now in this regime. So we have this thing called big data, where people have collected massive amounts of data and they've thrown that data to sophisticated algorithms, and that has resulted in some very interesting and results that we've seen over the years as well, right? So people tend to ignore physics in this region and think that somehow, some people, of course, think that we can get rid of all the physics that physical knowledge that we've accrued over the years and, just work with big data. So I'm going to talk about something in the middle. So where we know some about our physical systems, and we also have some data. Now, how do we merge the two and leverage these machine learning algorithms, okay? So that's the topic for the talk today. Let me just introduce you to this idea of physics-informed neural networks briefly before I go on, just in case, just to be everybody on the same page, okay? So the question is, how can you use a neural network to solve a partial differential equation, for example, right? So we may have heard of, solving a problem by collecting a lot of labeled data sets and trying to, let's say, approximate the behavior of that physical system. But if we have an equation, a partial differential equation, for example, can we solve it using a neural network? So essentially, it works the same way as a supervised learning algorithm works, except the fact that it is not supervised learning. So let's say we have this partial differential equation and this unknown variable u, which is a function of two variables x and t, x being, let's say, spatial variable in this time that it depends on, and we have some PD that rates u to x and t, and we want to find the solution of u for some domain x and t, right? And the way we do it is, let's say we would randomly initialize our neural network, and we'll feed, let's say, a bunch of values x and t, and we'll say, okay, what is the value of u that it predicts? Of course, it's randomly initialized, so it will predict something that is total garbage, right? And most likely not satisfy the partial differential equation. But at that point, what we need to do is we need to plug the solution in the PD and see whether this is a good solution or not. And for that, we need partial derivatives of u with respect to the input variables. Now, how can we get that? So all who are familiar with neural networks, you know something called propagation that you can use to compute the sensitivity of your loss function with respect to these here of these connections, right? Similarly, we can compute this derivative of u. We can go all the way back to through these inputs and compute the derivatives of u with respect to the inputs x and t. Same idea, chain rule that we use in backpropagation. And therefore, it gives us all these partial derivatives. You want second order derivative or higher order derivative or first order, whatever. And then you plug this into the residual of your PDE, right? So you take everything to the left-hand side of partial differential equation, that forms your residual, and you hope that if my solution is correct, the residual would be 0 everywhere in the domain, right? That's when you can say that my neural network has learned to predict the solution in the domain, right? But typically it will not be possible in the first iteration, so you would have to go on and continue this learning process. But additionally, often when we are solving PDEs, we have additional, let's say, constraints or information, which in the form of boundary condition or initial condition and some maybe observed data we have at some sensors, right? So we could all plug that in here and add a residual term, and we try to optimize or learn the weights of these neural networks based on this combined loss function, right? So initially, we would have to do several iterations. Our hope is that eventually it will be able to give us a solution that may not give us the residual that is exactly 0, but somewhere close to it, right? That is typically the case. And at that point, we can say, yes, we have learned, our neural network has learned the solution, and now we can use it to predict the points that it was not trained on. So there is oftentimes when I present this, people have this confusion that, okay, how much data do you need to train this, right? We don't need any data, by the way. So you don't need any data for training this because the training is controlled by the PDE. So your PDE is guiding the training, similar to in your supervised learning. Your labels are guiding the training, right? So even if it's 0 data, no data available here, this is the data part. You can still train. I'll show you some examples of it. And that's the forward modeling part. Oftentimes in computational sciences, we don't have any available data and we just want to do forward modeling for given parameter set. And that's possible as well with this. But of course, there are some challenges associated with it and some, let's say, positive aspects of using this approach. And let's talk about that now. Okay, so let me give you an example of solving something called the Eikonal equation. Now, you may have a different PDE in your field that you are interested in solving, but I'll show you some, let's say, share my perspectives in this example, and then I'll show some other PDEs. And of course, there is a particular PDE in your field that you are interested in, and you are interested in solving. You could also use pins for that, and there are chances that people would have already done that, and you could learn from that experience of others as well and move forward from there. Anyway, so the Eikonal equation gives you the first arriving time from some, let's say, source in the subsurface. So let's say this was the, let's say, location of the earthquake, and the waves propagated everywhere, you know, in the domain. And you are interested in computing these travel time it took for this wave to arrive from the source to a point on the surface, right? So your Eikonal equation will give you that. So this is a first order partial differential equation, and T, capital T, is the unknown, which is called travel time. V is phase velocity in this domain that this wave is propagating in, and we have a boundary condition that the travel time at the source location is 0, right? So we treat the source as the point where this energy originated, and therefore all the travel time is relative to this 0 value, okay? So how can we show this using physics-informed neural networks? So let's say we have this sort of network where you have arbitrary number of hidden layers, and this is your input layer where X, S, Z, S are your source coordinates. Okay, so this is the location of your source example, and this is the location of a particular receiver, and you can create many such pairs of source receiver pairs to train this model on, right, with your computational domain. And the idea is that once trained, this neural network can give me this travel time value given source receiver coordinates. Okay, of course, if you have a 3D problem, then you can add one more on for the y-axis of the y coordinate of the source and y coordinate of the receiver, right? So that's essentially what we do: collect a bunch of source receiver pairs and train our network on that, and hope that it will learn this function that relates this to the travel time value. The way we would do it is we would form the loss function based on two terms, no data, One is the iconal residual, the residual of the iconal equation that you see here, and the other is the boundary condition. Okay, so that's essentially what we do here. And we can go to the detail of training and stuff in the Q&A session. So let's move on. So here is an example. Once trained, you can then use it to predict solutions. So what you see here is the velocity model in this color. So it goes from 1.5 kilometers per second on the surface to about 4.5 kilometers at the bottom. It has topography, and this is the result with a conventional method.
Sorry to interrupt. Can you edit the view mode, the presentation mode, and enter it again? Because I believe the pointer is important for the or online on. So maybe hit escape here and then enter it again. Yes,
Screen sharing is stopped.
that's fine. You can share the screen now. Just PowerPoint. Yes, and then and then maybe
Let's see.
no, actually it's
Can we get,
yeah.
can we get this or no? P? Just P. Nothing happened.
For some reason it's
No, anyway.
we tried.
Yeah. So yeah, so this is the result of a conventional method, fast sweeping method, and this is the result for pins. So of course, this is the errors that I plot here, and you can see that the errors for fast sweeping that is much larger than what you get with pins. So at least it shows that we can solve using pins the actual equation and also get a solution that is, let's say, quite accurate. Again, it's weird, right? Yeah.
I think you need to use the keyboard for clicking because we cannot hear as the viewer. We don't see the point for online. Only us here can see it. So
okay, let's use this.
Yeah.
All right. So I'll try to use my words to indicate where to look. Okay. Thank you for your patience, everyone there. All right. So at least we can check one box that we are able to solve the iconal equation using pins. But what else can we do with this, right? This is just the start. And why does it matter? Right? We already have a method that can solve, that can give a solution. Why not just use that with a very small grid, and that could give us, probably an even accurate solution, right? So here is one more thing. So conventional methods have this limitation that if you have used it to solve a problem for one velocity or a particular source location, you need to spend the same amount of effort to solve a different problem, for example, a different velocity model, or if you change the source location. Whereas with pins, what we can do is we can use the knowledge that we accrued by solving the first problem and use that knowledge in the second problem. So what you see here in the bottom, let's say, graph here is that in blue is shown when you train a neural network to solve a problem, and initialize it randomly, then it takes plenty of time to converge, right? A number of epochs it takes to converge. But once you have solved this, then you solve a different problem, starting with the weights of the previous problem that you had solved, and it converges much faster, about 1/5 of the time. And that is one aspect that is different than conventional techniques, right? And there have been a lot of analysis we did this that you could see on the paper mentioned here, which was published in 2021. And you could look at, we compared, if you have, let's say, X number of sources, then pins become much more efficient than conventional method. As if you have one or two sources, then pins is still computationally more expensive than conventional method. So people will ask, why is there, what is the point of using pins here? Is that, when you're solving large scale seismic pins, then you can speed things up a lot using pins. So that's just one aspect, right? Speeding things up. And we'll talk about more. All right. So when I was a PhD student, I spent about 1.5 to 2 years solving what is called the anisotropic iconal equation. So it's the iconal equation that corresponding to some form of the Earth, which we call anisotropic. Anisotropy means it has a different speed of propagation in different directions. Okay. So when I was doing my PhD, nobody had solved that problem, and people had some approximate solutions for it. But then it took me a while to really come up with a way to solve that using what is called as the fast sweeping method. The pins, it just took me changing 2 lines of code. Okay, why? Because all the structure of the algorithm stays the same. You just replace the old PD with the new PD, right? So everything stays the same. you have now new PD, you plug that in. Pins do not know, whether it's an isotropic iconal equation or isotropic. Its job is to just try to minimize the residual of the PD, right? So essentially that gives you a lot of flexibility, right, to solve more complex problems, and it starts to become more attractive. So we did this analysis and published a book chapter, and we mentioned about a lot of other things. For example, if you have a code, for example, in fast-moving code that you had written for your, let's say, running on CPUs, and now you want to utilize GPUs, you have to rewrite that code. Whereas because this is based on TensorFlow, it does not care. It runs on whatever the underlying architecture is, and you can use the same code essentially for speeding things up on a different architecture. And there are other advantages of this, like you see this topography. This is not easy to model using conventional methods like finite difference. So people use something like mathematical flattening to flatten this topography layer, or they use some form of special grid. The pins liberate you of this terrain mesh generation, and this can be very interesting for many who are in the audience and are interested in using, for example, methods like finite element method, which require a lot of specialized grid first that you need to form or mesh, and then you can solve those your equations, right? So here you don't need to worry about mesh generation. This is quite a flexible method, right? We can go into the detail in the Q&A session of why this is the case. Okay, so one thing I mentioned was computational speed you can gain. The other is flexibility. Let's talk about something else, and this is more interesting than the two examples I showed for. Okay, so in 2017 we tried to solve another complex form of the iconal equation, which is called the attenuating VTI iconal equation. And this is so complex that I cannot write this equation on the slide here, and I have to write it in these coefficients that you see. And this is a coupled partial differential equation. So there are two PDEs that need to be solved together. So in 2017, we tried to solve this using conventional methods, and we failed. We tried hard, but we could not find a way to solve this using the fast sweeping method. It may be possible to solve it, but nobody has yet been able to. Guess what? The pins just need to change the loss function to this new partial differential equation, and it works. Okay, so that's one of the things pins can shine is if you have a PDE that people struggle with solving, or they come up with some form of approximation only to split, then pins can be really nice. And pins start to get a lot more computationally attractive if you have very complicated partial differential equations. And I have some examples here of the results, which show that the errors are also extremely small. You can read on the scale bar, right? So this is a, let's say, advantage that we can get by using pins. Now, some more examples of wave field modeling. So people in my field are very interested in seismic waves. So not just travel time. So what I showed before were just travel times, which gives you the value of the first arriving wave only. Okay. Now we want to model the wave field, and it could also do that. So here in this case, I show on the top left two tetrahedron model. So this is just a homogeneous background with just two rectangular scatters, and we want to solve for the scattered wave field, the wave field generated by these scatterers in an otherwise homogeneous medium. Okay, so what you see here on the top left is the 5 Hz solution, and the bottom, middle left is the 5 Hz solution, and middle bottom is the 8 solution, and the errors on the right hand side. Now you'll see there is some receive or errors in the solution, and that's one of the weakness of pins. If you have the underlying function which has some high frequency features, it struggles to approximate that, and that's because some of you already be aware of what is called as the spectral bias of neural network, that it learns the low frequency features of the solution really fast, but it takes time learning the high frequency feature. That becomes more of a problem for us in this case if we don't have any data to guide that learning. And just using physics, it is still an outstanding problem, something where I would invite all the people in the audience to this topic, because this is a research topic which you may contribute to as well. All right. One interesting thing we observed with pins was that people are familiar with this process of wave propagation know there's something called CFL condition that you need to satisfy to solve using conventional methods, right? So you cannot have say time step that is much longer than what is allowed by your grids to solve this partial differential equation using conventional methods. That's not the case with pins. As you can see, pins finite difference is unstable. When you put a source in the middle where we have high anisotropy, let's say sharp variations, whereas pins do not struggle with that. So that's one advantage of pins, because it's trying to build a global solution, and it does not build a solution starting from, let's say, one point to the other, which these conventional methods do, and therefore they need to propagate the solution, let's say, from the let's say origin where this is propagated. All right, so this is one attempt to try to address the computational issues with pins. So if you're trying to use pins to solve partial differential equations, and your PD is, let's say, second order or higher order, then you'll have a tough time in terms of speeding things up, or in terms of computational requirement, because you need to do this. So you need to do this automatic differentiation multiple times from the output to the input, right? And that takes up a lot of time if you have a deep neural network. And therefore, my goal here was to reduce, let's say, the number of, let's say, layers that I have here, and still try to make it work. So I reduced myself to 2 layers and said, okay, let me see if it works. And using all the activation functions that people use in the literature, it does not work. It just is stuck and it does not improve. It's stuck in some bad minima. It's not moving, or probably this network is not expressed enough, or it may take very, very long time to find a way to decrease this loss function. Whereas here, what we use is called Kronecker neural network, or it's also called the Rowdy activation function. So what it does is, and this is something that all you can use who are even not using pins, but you're having some problem with bad minima in problems, and trying to explore it from the perspective of activation function. So what it does is, it combines your regular activation functions like ATAN, ILU, and adds some sinusoidal noise on top of it. So if you have your solutions that have these features like sine and cosine, then this kind of activation function is found to help converge much faster. So it gets stuck for a little bit, but then finds a way to reduce the residual, as you see here. Okay, so this is just an example of how we are trying to address this issue of computational cost with pins. And of course, there is a lot of room to improve that. I'll talk about that a little bit in my last slide as well. Okay, so here is an example of scaling things up. So this is using pins to compute travel times at the global scale. Okay, so so we have this Earth model from the crust to the upper mantle, all the way to the upper mantle. So this is about 60 kilometers from the crust down to the upper mantle. And what we're trying to do here is to build a neural network that can give you a travel time from any earthquake location in the subspace to any receiver location on the surface. Okay? So that as soon as you have an earthquake, you can immediately run some inversion algorithms and find out the location, which can be used for earthquake early warning studies, or doing uncertainty quantification, which requires a really fast forward modeling engine. Okay, it took us 4 days of training this large pin model. And what you see here on the top left here is the vertically polarized P wave velocity. This is P wave velocity at a depth of 250 kilometers of the Earth. And this is the P wave velocity, but the recovered one from our travel time. So once we have trained our neural network, we compute the travel times, and we plug those travel times in the equation to get the velocity back, just to compare if we have learned the correct travel time. It shows a lot of the features that are very, very similar, except for some small errors, right? And if, of course, if we train further, maybe with a large network, we should be able to even reduce those too. But we analyzed that for our applications in general, this is good enough. Okay. Okay, so quickly I'll go over some examples of seismic inversion and show you how pins can be used to solve inverse problems too. Right? So far we've talked about solving forward problems where we don't have any data. Now you have some observations and you want to solve for some parameters of the subsurface, such as velocity. Now this network that I showed you when I was trying to solve the Iconal equation, this neural network was trying to learn the mapping from given some source and receiver coordinates to the travel time values. Now, what you can do is you can add another network, which we call the velocity network. And the job of this network is, given some coordinate in your domain, predicts the velocity, because velocity is independent of the source locations, and you combine the output of these two networks into a single function and train them simultaneously. So what is this first term here? This is data mismatch. So you have some observations on your station. What you're trying to do is you're trying to tell this neural network, give travel times that match this data on the surface. You have your boundary condition and you have your iconal residuals. I'm telling this network, okay, don't give me these travel times that just match the observations that I've made, but also satisfy the boundary condition of this PDE, but also satisfy this partial differential equation. And this partial differential equation, we have this velocity, which is being fed through this as the output of this velocity network, right? So a good thing about this is that typically in inverse problems, those of you who are involved in solving inverse problems, that in almost all cases our inverse problems ill-posed, and we need to do some form of regularization really to solve those inverse problems. Now, typically in cytotomography, people use something called what is called as smoothing regularizers. So they smooth, say, their gradients before updating their velocity models. And what it does is it reduces the resolution of the resulting velocity model, and moreover, smoothing does not use any understanding of our knowledge wave propagation. Now, if you have this iconal equation in the loss function, this acts as a fit-informed regularizer and tries to fill in missing information using the physics of wave propagation, which is a much better way of dealing with the problem of ill-posedness or non-unique. Okay? So here's just one example. This is your true model. We're trying to do some cross-hole tomography. So we're firing shots from here and receiving here. This is our initial velocity model, very different from, let's say, what is the true model. And this is because we are randomly initializing our neural network. And this is our solution, which gives us a smooth representation of the original velocity model. And this is basically what you can use for doing some full waveform inversion for building higher resolution velocity model. So here's an example of using pins to do full waveform inversion, which is a very challenging problem to solve in the field of computational seismology. Okay, so here is we see some examples of wave propagation at different time snapshots between the ground truth and pins, and some small errors. And just by using a single source, and about, I think there are 20 or 11 receivers here. So we're just trying to shoot from here and recording here. And this is the initial model. We are able to build something close to this anomaly just by using a single source. Of course, you can do better if you have more sources, right? But this is just an illustration of how you could use pins to do full waveform inversion as well. Now, this is an example of using pins to solve the hypocenter localization problem. So that's typically the first problem that people solve when your instruments record some energy from, let's say, an earthquake, right? So that's the first thing people do: record, try to figure out as quickly as possible where is this location. And therefore, based on that, there are earthquake early warning systems that send signals. For example, I don't know if you've heard about something called shake alert, which is being used in Western United States. And that uses the let's say, location or the travel time of the first arriving wave to alert people in that vicinity, so that when the more damaging wave comes, which is called as the shear wave, they can take some evasive action, right, to prevent themselves. And it leaves them with a few seconds though, but that's the best we do. So with pins, we are trying to do this process in a real-time sense, because timing is really crucial in the kind of problems, whether it's earthquake hazard or it is coming from induced seismicity problems, where you're trying to frack the subsurface, you're trying to induce these small earthquakes, and you're trying to ensure that they don't leak into some formations beyond where you want to let's say, create these cracks. And therefore, we're trying to use pins to do this in real time, and therefore we have trained this on some, let's say, synthetic data. We bring it online, and it then can predict using transfer learning in a matter of a couple of seconds. We can build the travel time map, and then we take the minimum of this travel time map to tell us where this source is. So I encourage you to read this application to get into more details of this. So there's just some example of showing the accuracy of it, and it works really well even if you have small number of sources, right? This is one of the good things that the reason why people cannot use shake alert in parts of the world is you need a dense array to do this, right? To do this signals, and this is not available in parts like Syria, for example, or Turkey, and therefore machine learning can bring in that thing where we could use information from sparse receivers by using physics of wave propagation in that, right? Of course, this is something that needs to run whether it works or not. Okay, so I mentioned to you there are some advantages of using pins, but there are some challenges as well. Now, where are we going forward this? So if any of you is interested, you're welcome to discuss this with me. But one thing you should also look at is the idea of operator learning. Okay, so far with pins, what I've shown you is that pins can approximate a function. Now, what we are trying to do here is we are trying to approximate an operator. So many of you know that a neural network is a universal function approximator, but it's not well known that it can also operate an approximator. That is, it can map from infinite dimensional function space to another infinite dimensional space. And that's what caught the attention of people recently, and they have developed this called as deep operator networks. And another competing paradigm is what is called Fourier neural operator. So essentially, we are trying to not learn a function, but a family of functions, so that if you have a velocity model, for example, that changes, then you would need to train pins again or retrain, right, using transfer learning. But now you hope if you can train for a family of velocity models, then even for a new velocity model, it should immediately give you the solution without having the need to retrain. And this is something. We have a couple of publication in progress on this, and hopefully we'll be able to show more results on this in the future. But this is an exciting direction that I would encourage all of you to look into. So what I've tried to do today is to demonstrate the applicability of pins on a wider array of applications pertaining to seismic modeling and inversion. Pins is not limited to seismic modeling and inversion. People have applied it to a whole, let's say, bunch of different applications, and it has really created this revolution in broad field of computational science and engineering. If you are interested in simulations and solving forward problems and inverse problems, look into pins and see what has been done already in your field. It has the potential of speeding up large-scale modeling and inversion problems. Of course, it has its own challenges, needs further research. Now, we're not saying that it is already better than finite difference or finite element, because those methods took 4 or 5 decades to develop and to where they are, right? Whereas pins, the first paper on pins was published in 2019. And we've been actively working for the past 3 to 4 years on pins. We have also used in many applications, but it's far from perfect. There are many things that could be improved in this arena. People who work on wave field modeling know that the boundary condition is one of the nuisance that you have to make sure it works well. And typically you have these absorbing boundary conditions on the edges of your model and the bottom, because try to simulate that these waves go out of your domain and do the flat path, which numerically is not possible to do that perfectly. And therefore, but with pins, absorbing boundary condition automatically taken care of, which is a very interesting observation. We don't understand the mathematical foundations of it yet, which we're trying to investigate, but at least this is based on our empirical evidence. Okay, challenges, low convergence. If you have a sharp heterogeneities in the velocity model, that results in high frequency features in your function. So anytime you have high frequency features in your function, pins will struggle to approximate those high frequency features, and therefore you need to figure out how to approximate that or solve the problem, either with using a large network, meaning causing you to spend a lot of computational effort, or some other ways. Hyperparameter selection, as of course all you work in machine learning are aware, it's another challenge. We are experimenting with the automated machine learning to try to look into this, how we can automatically select those hyperparameters. All right, I'd like to end my talk by acknowledging many of my collaborators who have contributed this work, and especially George Kanadakis at Brown University, who is also the main person behind PINS and DeepONet. And I'd also like to thank Dr. Allah Sultan, who's the Dean of Deanship of Research Oversight and Coordination. Because of their international summer program, I spent my time last summer the group of George Conrad at Brown University. And all of those in the audience, I'd encourage you to look into the program, which is a very exciting program, and KFUPM or Rock will support your travel to these places, and really grateful to them. For this, I'd also thank Chairman John and Dean Dr. Abdulaziz Kabi for their support and funding for most of this research. I think that's all from my side. So you can look up here on this webpage, or if you're interested in learning more about these several things which I showed just with one slide, you can go on and look at some of these talks on YouTube, which go into more detail, or you can contact me by email if you are interested in discussing about pins and seeing how it could help you in research. All right, and I look forward to other questions that you may have. Thank you so much, everyone, for listening. Let's tap this water.
Okay, thank you, Dr. Omar, for your informative and interesting presentation. Now I will open the floor for questions. Let's start receiving the questions from the attendees here. And for the online attendees, please, if you have any questions, your questions or raise your hand.
Well, thank you, Dr. Amir, for the interesting presentation. I actually didn't know that it's your summer with such a big name, and I believe this drives your motivation towards the pins. I think we discussed pins. Was it a couple of years ago when they were kind of published? But the progress that I see is really interesting. Two questions, if I may. The first question, you mentioned up two applications. One is the forward modeling, one is the inverse. Which one do you see from a pin's point of view is more useful, and I would say is difficult? Something that if somebody is planning on jumping on this, where do you direct them to start? Right? And the other question will come after. So.
Perfect. All right. Thank you, Mutaz, for the question. So people who are working in traditional field of inversion, what you have to do is they have to put together first a forward modeling engine. They have to repeat that forward modeling engine multiple times with different parameter setting and try to calculate the receipt based on their observations and try to update, let's say, whatever parameter I'm trying to invert for, right? So that's pins. What pins do is it does not work like this. So it has, let's say, one setup for inverse problems, and therefore pins are much more efficient when you're talking about inverse problems than forward problems. Okay, so I think inverse problem is the more challenging part, also because of this issue of non-uniqueness. And let's say I showed you an example of solving an inverse problem, but I'm trying to only invert for a single parameter. When you have multiple parameters to invert for, such as maybe you're trying to invert for velocity in the earth and density, there is a strong trade-off between the two. And that kind of problem I haven't seen being solved with pins. Okay, and that is something that I'm interested in personally, but it's going to be a challenge. But for sure, I think pins can contribute, or pins can be in the immediate future be more, let's say, impactful in the area of inversion rather than modeling. Now, it can be impactful in the area of modeling, for example, in studies where, for example, in our field, if you want to do uncertainty analysis, you have to have a really fast modeling engine. It's not possible so far because it takes a long time to solve these wave equations, for example. Therefore, if you have a model or a neural network that can immediately give a solution for, let's say, different representations of velocities, that's what probably you could do with operator learning. Then you could study this problem of uncertainty quantification in seismology or in other fields. That's what we are also trying to do. We have a project that is funded between ourselves and Brown University, funded by Shell. We're trying to learn a forward modeling operator for the wave equation, so that once it is trained and now you want to test different velocity configurations, you can do that really fast. But I think when you talk about pins, probably inverse problem is something that I would encourage you to look into.
Great, thank you. And just to comment on that, I believe two problems that are actually inseparable. You cannot just isolate one and say, well, I will only focus on inverse problems, or I will only focus on forward problems. At the end, optimally, they go hand in hand.
Yeah.
As you mentioned, in order to enable a powerful inverse engine, you still need a forward engine that can keep up with them in terms of speed. Okay, that's one of the bottlenecks. And I've seen this not only in this field in geoscience, various problems. It comes to the exact same setup where you have a forward kind of inverse problem. Recently, we heard a talk from Dr. Maad Al-Uwaifir on optimal power flow. He's from an electrical engineering partner. He's a fellow at the center. He was talking about this. How can you use pins for this optimal power flow? Almost similar setup. At the end of the day, it's partial differential equations. How can you solve them? Now, my other question, if I may, hopefully is related to this concept of pins in general. We see other variants. We see, or sometimes you see different terminologies like physics, physics and form, and I've heard others. What would be your kind of rule to put them all together? Is the one kind of more general than the others? Because if that's the case, I would put the root of it beyond or before 2009. Because you mentioned the very first publication appeared in 2009, right? So if any kind of physics guide, it would go way beyond that.
Right.
So what would be the rule of thumb?
I agree.
And also, how would you link the PIN and pins as a learning paradigm with the architectures of neural network? Currently, you didn't spend, or you didn't talk about this. Is there any specific architecture that pins do usually? Does it do well with simple ANNs, but not so well with CNNs or something like that?
Yeah. Thank you, Mutaz, for this question. So the first question you mentioned. Let me see, how can I phrase this? Let me answer your question first about architecture. So in terms of architecture, Mutaz, yes, only talked about this artificial neural networks or multi-layer perceptrons, right? But people have known that they've used other architectures like GANs, for example, in the context of pins, and there have been efforts to use CNN, but essentially, I think the bottleneck here is you need to figure out a way how you update the output variable with respect to the input. And oftentimes, with some of these architectures, it's not straightforward to figure out how you would do that. You go all the way from output to the input, right? So that's something that you do, right? So that would be my answer to the second question. For the first question, you are absolutely right that any form of physics, if you are trying to train your network some kind of physics, then it does not, it's limited to pins, right? Because in pins, we are explicitly telling to give us a solution that honors the equation, right? Whereas I've seen some efforts, or of course you might be doing some of those, where people are trying to embed physical knowledge in some different ways, right? And there have been other efforts, right? So of course, it can be done in different ways. So for example, I can show you an example here in my results. And so, for example, I'm trying to do this and solve this inverse problem, right? Whereas my initial model looks nothing like what a true Earth would look like, right? So this is a very bad initial model. A true Earth would never look something like this. It has layers. So that is also a knowledge that I have, that I know about my physical system, but I haven't been able to teach it, right? So so the question is, how can, let's say, embed that knowledge? So there could be multiple ways of embedding knowledge of your physical system into your neural network training. So I agree with you, Mutaz, that there have been papers in the past too where people have tried to embed the physics, and sometimes they do it other than pins. And it would be nice, I think, we don't get ourselves to just pins, but harness all of that information, like, how can, and oftentimes this is what people call inductive bias. So this is what also people have found with pins. It takes a lot of time to learn, some of these problems. But if you have some inductive bias embedded in your architecture, maybe the way you design your architecture, take into account some of that knowledge, can result in speed up of training, right?
Yeah, right. To the credit of the authors of the paper that I referred to in 2019, they're the first to formalize that framework. I would say all of this, it was scattered, where they basically just throw in kind of a piece of knowledge, but it's not a framework. After this paper, I think now it's a framework.
Yeah.
Back to you, Saddam. Sorry for that.
And maybe one comment I can make, and then Saddam, you can close this session. There are some people who are working on full waveform inversion. So what they do in the past, look at the waveform, give me the velocity model. That's hardcore data driven. Doesn't work well in terms of if you change the data a little bit, right? Now what they've done is they've added a layer of solving the forward problem. Right? So now they calculate the residual and then embed physics this way, right? It's not really embedding it in the physics in the pins, but there is another way to do it.
I have one more question.
Thank you, Dr. Mu'taz, and thank you for your questions, and thank you for your answers. Any other questions from here?
There is something in the
Can we get the chat?
Okay, thank you. We have questions here from the online attendees, especially from Dr. Asad Arshad. His questions: did you encounter optimized sensor placement issues for field reconstructions in your research? If yes, did you see the effect of using BINN to reduce error in comparison to our machine learning models?
Okay. So I think we don't deal with this sensor placement issue in this, but typically pins are a lot more, let's say, robust to this sensor placement issue, in the sense that because it has physics embedded in it. So it will assume that it knows something about a place where you didn't have a sensor through physics, right? Whereas if you use something that is purely data driven, which is not taking information from physics, that's a bigger issue in that. And we have tried to do some tests where we have randomly received sensors, for example, for our hypocenter localization or earthquake localization problem. And the results that we found were quite robust to that. All right, so that would be my answer. Thank you for your question.
Okay. Any more questions? I think no more questions. At the end, I would like to thank you, Dr. Umair, for accepting our invitation. And I would like to thank all of you for attending our today webinar and for your attentions. And looking forward to seeing you in our upcoming events.
Excellent. Thank you so much, everyone.
Bye.